Cameron Penn Clark. Cameron is with the Council for Geoscience here in Belleville in the Cape. Cameron is a whole lot younger than many of us and a full-blown sedimentologist, which is fantastic. We need more sedimentologists in this geological sector of ours. Anyway, he did his basic degree and then a PhD at the University of Witwatersrand, so he's also a Witsi, so we're balancing out the different universities as we go along. And welcome, Cameron. We really look forward to your presentation on the Bokkeveld. And we look forward to some discussion about these fascinating rocks, particularly the colors I find fascinating. So we look forward to some discussion at the end of your talk. Are you just going to go ahead, share your screen and run with it?
Yeah, no, definitely. So I'm just going to try and cast my screen now.
Yeah.
Where did I do
Hey, Michael. Dorma.
Thank you, John.
Yeah, good.
Okay. Is everyone able to see my screen?
Fantastic. No, you just got to maximize it.
Yeah. So I'm just going to change it now to, there we go.
Okay.
Is that better?
All right.
All right.
Everyone just mute their mics and switch off their videos.
Cameron, are you on slideshow? Are you on slideshow?
Yeah, it should be. Is it okay. Got the slideshow showing up or?
Yeah, okay, good. It's not full screen, but that's okay.
Okay, let me just see if I can figure this out.
Go to slideshow and then click on slideshow on your PowerPoint.
Yeah, so is it showing the presenter display or the...
Yes, it's the presenter display. You must go on slideshow, then click on slideshow.
Let me just do this first. Let me just...
John, what were you saying about the younger guys taking over easily?
Yeah, I'm the most computer illiterate millennial you'll come across.
Go back to where you were on the PowerPoint.
All right. Let me just start sharing the screen again. Okay. There we go.
Okay. Now click on PowerPoint. Click on slideshow. Up on the top. No.
On the top here.
No, on your PowerPoint presentation. Click on, go back.
I've got it over here because I mean, if I hit the slideshow button, it just shows up the presenter display.
There we are.
No, that's good. Now you're right. Now you're good. Yes, that's fine.
Corners, whatever happened, I don't know. Apologies, guys.
There you go. The youngsters can do it with a bit of help from the oldies. Thanks, Fred.
Yeah, definitely. Cheers, chaps.
Okay.
So, no, thanks very much. So, yeah, thanks very much for attending today's talk on the Bokkeveld group. So it's some stuff that I've been doing for the past just a long time. And yeah, it's become a bit of a fascination to me, this time period, the Devonian as a whole. So it all began as a master's degree, which evolved into a PhD, which evolved into 2 postdocs, and now I'm continuing research now at the CGS on this. So this year is the Bokkeveld group in all of its glory at Groot-Rivier Hoogte in the Cederberg, and this is the type section, so very beautiful rocks. So I just want to do a brief recap of what happened during the Devonian period. So the Devonian period, you had 2 large supercontinents. You had Gondwana towards the south, Laurisia, or your Euramerica, depending on what side of the Atlantic Ocean you sit on, to the north, and then the small microcontinents of Siberia. And throughout the Devonian period, Gondwana was migrating northwards towards Laurisia, eventually colliding, caused enclosure of the Rheic Ocean, and then over time the Paleotethys Sea also sort of got like something stuck in a zipper, and it got zipped out. So throughout this time period, Gondwana was moving northwards. If we look at climates throughout the Devonian period, climates were more or less equitable, sort of like what we have today, where you've got clearly defined latitudinal belts. But what was actually what is interesting about the Devonian is that it was a hot house world. So there were no large polar ice caps for most of the Devonian period. It's only towards the very latest Devonian that during the Flaminian when one starts seeing the development of true polar ice caps at the South Pole. But it's quite anomalous because you have this large continental area mass at the South Pole and no ice caps. So my fascination is around non-polar, polar environments, siliciclastic deposits. So they're very interesting. So
Cameron, just give us a context, the Devonian, you're talking about the age span of the Devonian for us people who don't work in the numbers like you do.
all right, so I'm in the triple digits of millions of years. So it's around about 420 to 360 million years ago. So yeah, not even last night, long ago. So yeah, it's a middle Paleozoic. Then if we have a look, also during the Devonian, what is quite interesting. So from a biological point of view, okay, it's just for perspective. South Africa is right at the cut end, so right in the southern parts climates. But what's interesting about the Devonian is that we see the rise of plants. So the earliest plants will take root on land. These eventually diversified into the first forests at the end of the Devonian period. So over a period of about 160 million years, we went from nothing on land to things on land. At the same time as well, very early arthropods invade land at the exact same time. So you've got the start of the first modern, or semblances of the first modern terrestrial ecosystems. In the oceans as well, there were great proliferation of life. So ammonites or ammonoids make their appearance. You also have the appearance of true sharks, ray fin fish, as well as fleshy fin fish or low fin fish, so coelacanths, they make their appearance. And these are alongside these other older existing orders of fish, so acanthodians, agnathans, so agnathans like this chap over here, he's got no jaw, and these big placoderms, which are the big monsters, I guess, of the Devonian oceans. Unfortunately, these oaks got clupped at the end of the Devonian period. They didn't make it through, unfortunately, which would have been quite cool to see them. I mean, I could do with other animals not being around like hardy-dars, but I'd easily sacrifice them for placoderms. But out of interest with coelacanths, or with fleshy fin fish, is that these diversified through time into alpistos so and then eventually into amphibians. So you got this tiktaalik, which is a sort of go-between. So and these eventually became tetrapods, and we are tetrapods. So we have our origin. We are all fleshy fin or coelacanth grade tetrapods, or tetrapod grade coelacanths. That's the correct way to say it. So we have our genesis during the Devonian period, and at the end of the Devonian period, these chaps went from very humble aquatic beginnings and eventually moved on to land. So a lot of stuff went down during the Devonian. And then from a sedimentological point of view, throwing life into the mix really changes things up quite a bit for sedimentology, and environments sort of evolve in response, that they feed off one another. So in the oceans, we've got a large, we see a proliferation of biogenic reefs. So you can see over here, during the Devonian, this reaches its peak. Lots of corals make these things balloon. They're just about everywhere except for the poles. And then at the same time as well, we see the rise in terrestrial ecosystems. So with plants coming onto land, you have the formation of soils with roots, you have the formation of soils, you've got new biogeochemical pathways to weather and erode rock and so forth. So we start even seeing changes in fluvial systems, so moving from braid plains to lazy meandering river systems, and these seem to increase through time. And this is pretty much the mode what we've got today in most areas of the world that are vegetated. So it was quite, you know, it's quite lacquer. Plants, you know, as much as they, you know, just stand there, they do a lot of stuff to help us. During the Devonian period as well, with all this life coming about and these changes in biogeochemical pathways, we see that there are a lot of these minor and major extinction events which haven't really been well documented. So there's plenty. So you can see through time, you know, right from the beginning up towards the late in the Devonian period, there were a hell of a lot of extinction events, and you see lots of faunal turnover, but we don't really know what the mechanism is for this. So these things were usually short-term. They usually occurred in the marine realm. They're usually associated with plankton and nectar blooms during transgressive phases. So we don't know what it is, but it seems as if effects that were happening on land, so with plants sequestering nutrients and all those goodies, holding that stuff back, it seems to have affected the marine environment. But it's something I'm busy investigating now with colleagues at Durham. So hopefully we'll have some sort of indication at the end of this year, or at least for South Africa. So in South Africa, we're actually quite blessed. You know, we've got most of the Devonian exposed in rocks of the upper Table Mountain group, Bokkeveld group, as well as the lower Overberg group, and then the very enigmatic Nsakaba formation as well, which is here in southern KZN. So why is it important to study these rocks? Well, South Africa was located at high latitude. So we were located between 60 and 90 degrees south. So we were sitting right at the South Pole. And most of our understanding about whenever you see these models for environmental change and ecological change in the Devonian, most of them are from low to temperate latitudes. So we've got quite a long-term record, and yeah, very good outcrops with respect to South America, Antarctica, and the Falklands. So Antarctica, it's under ice. Falklands, the Argentines make it too bloody expensive for us to go out there. And in South America, the stuff is vegetated over and they don't speak English. So it's very difficult to try and set up working relationships there. So just to go into life at high latitudes. So we know high latitude environments from what is going on today. So we know from ice house worlds and not greenhouse worlds, a lot of our models. So we are used to this sort of picture of, you know, snow, ice, glacial processes. We are not used to anything that's non-glacial, to understand. So at high latitudes, solar irradiance is much lower than at the equator, so it's cooler overall. And if you remember this diagram from school and university, you know, the sun has to clup through more of the atmosphere than what it does at the poles and at the equator. So solar irradiance is lower. Primary production in the seas are seasonal, but they normally are greatest. So oceanic differences in density and temperature means that all this goodness is kept behind, and only seasonally does it penetrate up into lower latitudes. So, but you do see seasonal tempos and removal of nutrient-rich waters through time. So, and then also as well, you've got periods of extended sunlight and periods of where there is no sunlight, and you know, this can be quite detrimental. If any of you guys have ever watched that horror movie flick 30 Days of Night, do yourself a favor. Thank God there are no vampires. You don't live at the poles, or should be charred. Then also at the poles, precipitation overall is lower. So this is just a graph to show average precipitation. But also as well, mechanical processes dominate chemical processes for weathering. So a lot more abrasion, a lot more attrition sort of processes. So you don't really have any of these funny chemical oxides and hydroxides that form, as well as carbonate. Carbonate is also pretty min. Then at this, if you also think about it as well, storms are different at high latitudes to what they are at lower latitudes. So storms tend to be seasonal. These are dominated by frontal systems. So mid-latitude cyclones is what we're going through now, or experiencing here in the Cape. The effects of tides are very minimal, so to find any tidal environments is quite significant. And then with Coriolis force, even though you've got these very big tropical depressions that form at low latitudes, the Coriolis forcing and deflection is minimal. So these storms, if you had the same sort of storms happening at the poles, these things would be more powerful. But here, mid-latitude cyclones and storms at the pole, Coriolis effect is at its greatest over here. So there's more spin in their steps. So you've got stronger, more frequent storms. And also these storms can have a larger effect deeper in the water column than what they would with say, for instance, a tropical depression or a cyclone. And because all of this, polar climates are more sensitive to global indicators of changes in eustatic trends, temperature changes, etc. And this is what we're seeing now, what's happening at the poles at the present day. Very, very insignificant, or seemingly insignificant changes in temperature are affecting the poles in a very detrimental way. So going back to South Africa and our talk, so this is the Bokkeveld group in all of its glory. We've got two large basins. We've got this Clan William sub-basin, which is towards the west. So at 21 East, you've got this change over in depositional style and stratigraphy. So you've got this western Clan William sub-basin and the eastern Agulhas sub-basin over here. And the main difference where these things have, you've got differences in thickness that one sees, differences, some subtle differences in paleo environment, but the big thing is up here at the tail end, the Bido and the Trucker subgroup are very different, and I'll go into that in a bit. So just in terms of time, so this over here is, I've been working now doing a biostratigraphic study to try and revise the time scale somewhat, because you don't have anything that's datable like volcanic tuffs and the like to try and date these rocks. So essentially these rocks over here, the Bokkeveld group from the fossils, these are probably latest Emsian, so latest early Devonian to middle Devonian to Juvetian in age. And this is just based on all of these different fossils, and these of course are a summary of the environment so that we are going to be looking at. So the fossils that one expects in the Bokkeveld group, these very sort of, there are some fish over there. These are poorly studied and poorly known, but of interest, the earliest known shark has been found in the Bokkeveld group. So that's quite cool. We've got trilobites, crinoids, these sort of invertebrates that you'll pick up now and again in the Bokkeveld group. Also some of the earliest plants known from Gondwana. These are the very early xylophyte Tutoitia. And then moving up in time, what we are seeing is that you've got some of the earliest forests known from the Devonian of Gondwana. So this is of this Archaeopteris tree forest. We've got these very early algae, and what's also interesting, earliest lamprey and earliest known scorpions are known from South Africa. Little known fact. So U-oaks are more attuned to seeing these sorts of outcrops, these highly weathered, highly leached. This here looks like it's some overturned bedding from what I can gather. These sort of outcrops, and as John says, lots of nice, wonderful colors, and these are due to these secondary oxides that have formed, that have, you know, weathered out. Some of these things I'd actually like to investigate in future as well, just to see if these things could be, you know, we would expect to see VMS type deposits, maybe even SEDEX type deposits in these sort of depositional environments. So it would be good to look at these again. But that's a story for another day. But I'm more used to these sorts of outcrops where weathering is near minimal. So this is at Gamkapoort Dam. So this is Bokkeveld group over here. It looks quite cool. You can see the full stratigraphy here. But just to show you the stratigraphy in the Bokkeveld group in its type section. So this is what it looks like, typical Hogsback topography, these alternating shales and sandstones. And what's nice is that in the, I think, you know, my predecessors, Hannes Teron and co, for mapping these things out lithidemically, so it makes life very easy. So we're going from the base, the Gedo, Gamke, Voorstok, Hex River, Tratra, Boerplaats, Warboenberg, Wuppertal, Klipbokop, Osberg, and Karoopoort formations. So here you've got a beautiful, beautiful exposures of the succession. And according to the old timers, these all formed upward coarsening sort of depot cycles, major depot cycles, which were thought to be repetitive progradational regimes within the basin after successive downwarping or transgressive events. And this is what I've been looking at. I've changed this a little bit, but we'll get into that in a bit. What we also see in the basin in terms of looking at thickness changes throughout as a general trend, sandstones tend to thicken towards the north, and mudstones tend to thicken towards the south. And at the changeover between the Clanwilliam and the Gullis subbasin, the Wuppertal formation, which we see in the west, seems to disappear. It doesn't seem to continue into the Gullis subbasin. It seems that the Wuppertal and Warboenberg formation probably merge at some point and change over into the shell that's in the east, the Curries formation. But the Curries as well has got this sort of sandy siltstone layer or horizon in the middle of the formation, which I think is an equivalent of the Wuppertal formation, but that warrants investigation another stage. So from all of this, these data, this is what the original idea for the Bokkeveld group was, you know, thought to be. You had a series of these deltas which prograded into the basin. You had this Clanwilliam Seaway, and which was more shallow than the Gullis. The Gullis was more deeper. But what's interesting as well is that where you've got these changeovers, these changes in thickness and in depositional trends, these tend to occur along what we think of these pre-Cape basinal highs. So here in Cape Town, Worcester area, the Stettin rise, which is coincident with the Stettin's anticline in the Cape Fold Belt, which manifests today. The Tankwa rise, which in the very earliest Karoo supergroup, we see the Tankwa rise also being a depot or a basinal high which affected the very early phases of the Karoo basin. Then we've also got the Swartberg rise, which is around state level. And again, what we see as well are these very funny changes in thickness. And then also, these also manifest in the Cape Fold Belt itself. So the Oudtshoorn Basin is located in this little sort of region between the Tankwa rise and the Swartberg rise. And then also as well, we see there's this massive deepening of the Cape supergroup towards Port Elizabeth. The paleoflow vectors from previous ideas, we think in the Clanwilliam Seaway, this was from north to south with minor components coming from the west, and in the Gullis Seaway, pretty much going towards the southeast. So the previous model that I sought to try and reassess was by Tony Tanquard and John Barwas. And what they had this deltaic, Solomon wave deltaic model that they proposed for the Bokkeveld group, where essentially each of these upward coarsening successions would be an upward shadowing of one of these Solomon wave deltas. So the lowest parts, the shells, would be these offshore pro-deltaic environments, which would grade upwards into these more proximal delta front deposits and so forth. What's interesting is that these delta plane environments were seemingly missing, which they equated, they thought that these things were reworked and or transgressively removed. there are quite big problems with this model, in that some of the stuff that was shown in this model you don't see in the field. So they mention that you've got these washover fans and these tidal inlets and these shallow estuarine channels, but you know, they mention it in this model, but it's not mentioned in their actual the text of the model. So there were big problems with this, and one of the big problems that with this model is that they assume that each of these coarsening upward successions were uniform. So you would see the exact same succession repeated of environments over and over again. So if we had to go back in time, according to this model, if you went scuba diving off the coast, this is a sort of what you would see. Probably no coral reefs. A lot of these other hokos and nunus swimming and crawling around. And then you'd have these very early plants that were inhabiting these more proximal environments. So what's also another pet interest of mine is the paleontology of the succession. So we've got these fossils of the what was formerly known as the Malvino-Caffric realm. I've just recently revised this now and decided we need to revise it because it's a racially charged term to the Malvino-Clausen realm. And we've got these highly endemic trilobites that lived in this region as well. So found here nowhere else. These also more cosmopolitan echinoderms. So here you've got a little brittle starfish that's blooming on the head of a trilobite. So that's quite cool. These very early fish. So this is the neurocranium, the brain cast of this very early shark that's known from the Bokkeveld group. These conularids, these were like sessile jellyfish. If you could imagine taking a jellyfish and then flipping it upside down and then putting it on the sediment, sitting on the sediment, that's what they would have looked like. Some crinoids, and then my pet love for all my sins are brachiopods. I don't know why, but these oaks are also very endemic, and without them, we won't be able to make any sort of correlations across Gondwana, which I'm working on as well. So what's interesting as well is that at the effects of climates, environments, etc., meant that all these organisms lived in very distinct regions. So in previous models, they proposed that there were three large realms: this Old World realm, which was located around the equator, the Appalachian realm, which was located at mid-latitudes, and what was known as the Malvino-Caffric realm at high latitudes. We've just recently, when I was doing my postdoc at Durham University, we reassessed this as well and did a huge statistical, very boring stuff. And we proposed that what we're actually seeing now is that the Malvino-Clausen was at super high latitudes, and that these sort of intermediate latitudes, we've got this new realm, the Amazonian realm or bioregion, but this is coming out later on this year. So it's also interesting as well is at high latitudes, remember I said that these things are very sensitive to changes in global tempos, and what we are actually starting to see now is that these oaks were successively being clucked by something, and they disappeared towards the end of the middle Devonian. So, and then going to late Devonian, you start seeing more mixing throughout, more cosmopolitan faunas. But this is directly related to environment, which is coming up. So back to the rocks. So I work mainly in the Cederberg region, which is this region up here. And I looked over a large sort of area. I think there's about 76 square kilos in total, where I looked at the sedimentology and stratigraphy of these deposits. So this is just a simplified geological map of the area. And in the field, so this is looking towards the south. There's the Bokkeveld there. This here is the Table Mountain group. And here going into the Oostvlei Hoogtes is the Witteberg group. So these rocks are exposed within the Cederberg monocline or the Cederberg anticline of the western branch of the Cape Fold Belt. and it really makes for some very spectacular scenery, especially the sunsets. This is the advantage of these, when these fronts come through, if you're there at the right time. This is, yeah, when the warm front pushes through, and they make some spectacular sunsets and scenery. Oh, and there's just to show you this stratigraphy over there. Sorry about that. So what I did was I measured these sections and I described the sedimentology thereof. This is just a simplified stratigraphy and environmental partitioning of the successions. So this is the series subgroup. And then that, of course, this is for the Bido subgroup. So what I did was I looked at it in its entirety, and it was a lot of work. I went mad from it. I think I still am. So what I noticed is that we have to look at these things in terms of lithofasces and their associations and environments and what have you. There are 8 large groupings of lithofasces associations, which have 12 lithofasces that were described. And these can be constrained within 3 large depositional systems. So there's the storm and wave dominated shallow marine depositional system, which is pretty much what we've got going on now around our coasts. So comprising most distal offshore environments moving upwards into these transitional environments, offshore transition zone, getting more storm and wave action. This is the lower shore face and eventually up into the upper shore face and the beach sort of environments. These transgressive barrier lagoon depositional systems, these are quite interesting in that these are the first and only known high latitude deposits from the Devonian that are known. And these wave influenced deltaic depositional systems. So Hannes, Tony and Co weren't exactly entirely wrong that there weren't deltas. There were. I mean, we've got deltas today for Pete's sake. They must be somewhere. So we managed to find some of them. So starting with the storm and wave dominated shallow marine depositional systems, these are the most prolific throughout the Bokkeveld group, let alone the Bokkeveld and Overberg group itself. So the only places where one doesn't see these sort of deposits is in the Kratra and Boerplaas, but stand to be corrected, we do see some of these manifestations down the Kratra formation with new research. So they're by far the most common depositional systems. And what's actually quite cool is that these individual environments can be traced out throughout the basin. So as a general trend, as we're moving north in the basin, is that these more proximal shore face and beach environments are more common. Moving towards the south, these more distal marine environments are more common. So that's actually fits the model that this basin is deepening towards the south. So this is just a summary of these environments and what one would see. I'm not going to spend too much time on this, but essentially offshore, clayey, silty, muddy, deep marine environments. Moving into the shore face environment, we start seeing the activity of storm wave base. So we start seeing more storm deposits in the most distal regions of the shore face. The upper shore face, you have more fair weather, day-to-day wave activity taking place. And then the beach, we all know about the beach. So I won't spend too much time on that there. But what's quite cool is that in shallow marine environments, you've got a whole bunch of you can have a look at the full spectrum of fluid dynamic processes that take place, and these manifest as different deposits in the rock record that you'd see. But also another pet project of mine is ethnology, so looking at fossil spoor, and you also see changes as well, but I'll go into that in a bit. So this is just a picture of what one of these upward coursing successions looks like in the field. So this at the top is the Hex River Formation, and here at the bottom, this is the Voorstorp Formation. So one can see that there's an upward increasing in sandstone content to the layman, but to a sedimentologist, what I see over here, I see that these big chunky upper shore face beach deposits, these more proximal lower shore face deposits, these amalgamated special type of sandstone, and these non-amalgamated sandstones at the base, which are offshore transition to distal lower shore face deposits. So starting at the bottom of the sedimentary pile, These are what these offshore environments look like. Again, as I said, you've got it's just shales for days. We've got these very interesting carbonate nodular horizons, which I'm trying to get people to more geochemically inclined folk. I don't like chemistry, but yeah, that's another story. But to have a look at these, so these are actually quite interesting. They only form in these environments. Got also these cool detached shore face deposits. So these are very short-lived, very sharp regressions that took place in the basin. So these forced regressive surfaces, and you've got these sandstones that were just dumped into the basin. So these are quite cool. We're also seeing as well what's interesting with the trace fossils. You've got very low diversity trace fossils, but if you know anything about trace fossils, you can use these fossil spore to try and work out when you had periods of anoxia or well oxidated water columns at the time. So, you know, this is pretty much what they look like. But what's quite interesting from a paleontological point of view, this is where you find all the fossils on these deposits. So this is of a cool trilobite I found a few years ago, and this is of a bioclastic coquina made up of brachiopod fossils. So as you move up through this pile towards the top of these deposits, you start seeing these storm scours coming into the basin. And these are precursors that you are starting to, of approaching storm wave base. And eventually when you move into the offshore transition zone, to the distal lower shore face, one sees more of these sandstones coming in, interbedding among these shales. So that's pretty much what it looks like. And these things are very sharp based, and there is a specific bed form called hummocky cross stratification, which in South Africa, you know, seems to be a word that people seem to, you know, just hate. Like, oh, there's no such thing, but there is. Here it is. So these are very good indicators of storm and wave activity. So, and they normally are sharply intercalated amongst these shales, but these shales are heterolithic laminated. You start seeing a lot more sand coming into the system, more high energy conditions. And if you go and you put your nose on one of these non-amalgamated hummocky cross-stratified sandstones, what you would see is that you've got multiple hummocky cross-stratified bed sets, some wave ripple lamination as well, which is also very indicative of wave activity for these things to form these symmetric ripples. And these shells themselves, as they get more sandier and they're approaching storm wave base, one starts seeing hummocky cross stratification even forming in these shells themselves. So that's quite cool. What's also quite lacquer as well, you know, you would come up to this and think, wow, my word, there's a channel. Look at it. And you'd think, that's quite cool. You've got these subaqueous channels. What's actually quite interesting, again, if you look at the sedimentology of these, if you look at what they look like, these things are actually very large storm scour beds themselves. So yeah, these are quite cool. These are also the first known high latitude massive storm scours that have been documented from globally. So these things are quite cool. So yeah, and then also as well, if you put your nose on them, you'd also see that these things have been secondarily reworked by wave action or have been reworked again. So more hummocky cross stratification, more wave ripple lamination, etc. Then from a biotic point of view, you can see as well, this is at this is from the base of one of these hummocky cross stratified sandstones. And this is a storm shell lag. So these little oaks got moert in these storm waves. They got broken up to bits. They got incorporated within these sandstones. So they form these lags at the base of these sandstones. And you can see all these fossils have been disarticulated. So normally these are preserved as casts or molds. So these things have been ripped apart. What's also quite cool as well, you've got some plant impressions. These plants were probably blown into the basin during these storm events and eventually buried. But what's also quite lacquer, if you could imagine, the sediment is being turned up quite a bit by by non-biogenic processes. And because of that being tilled over, it's very rich in nutrients. And if you look in shoreface environments today, they're the most bioproductive regions on Earth. And what's quite interesting from a trace fossil point of view is that you can see that there are all these traces, these sort of what you'd associate with the Zoophacus, or Zoophacus cruziana ichnofacies. So these hohos and nunus were chawing the sediment dick over here, and it was a good time for them. They were really enjoying it until they went extinct. So very, very bioproductive regions, and also the Bokkeveld group has got a spectacular array of trace fossils. So I'm going to be working with a group from Saskatchewan University sometime in the near future to actually document these things in more detail. So then moving sort of, if we continue going up these sedimentary piles, we eventually intersect the proximal lower shore face. So in the field, this is what it looks like. So you've got these non-amalgamated storm deposits. These things become more amalgamated into these more thicker amalgamated hummocky cross-stratified sandstones, quartz wackies. And yeah, they're quite cool. You've got these very big storm events. So if you can imagine, this in the proximal lower shore face, this is where these storm waves move the shore face more frequently and more rapidly, reworking, winnowing the sediment back and forth. So it's quite cool is that you even start seeing different flavors of hummocky cross stratification. You just go back. I thought that was a little interpretive sketch. So you start seeing this sort of anisotropic hummocky cross stratification. So right at the top of these piles, so you can actually start seeing where fair weather wave base is starting to rework hummocky cross stratified sandstone. So this is very, yeah, this is, for a sedimentologist, this is cool. And then you also start seeing soily cross stratification, which is also quite cool. So this is a very nice indicator of more proximal, more intense storm activity. And then finally moving to the upper shore face beach. If John, you talk about colors, and yeah, you can see this also based on color in the field. You've got these proximal lower shore face quartz wackies, which tend to be dark gray in color. Moving to the upper shore face beach, where these things are more, lighter peachy colored in the field. What's quite cool is that you've got a changeover in bed forms. So you've got tabular cross bedding, planar lamination, as well as trough cross bedding. So what's cool is that you see these trains of dunes that were probably pooled in the alongshore drift direction parallel to the coastline. So that's pretty cool. So again, you can see the whole spectrum of shallow marine processes in the Bokkeveld group. From a biological point of view, we see as well, there's something also very strange with the Bokkeveld group. Probably it's a high latitude thing. Is that we see that you get more of these Zoophacus type trace fossils when you should be getting these Silonechnus type trace fossils. I won't go into detail with that, but there's something weird going on here. So he has a nice Zoophacus that's been cut in half. Cochlichnus, Asterosoma. But what's also interesting as well is that if you move into these more beach environments, probably the more backshore environments, we start seeing these probable plant rhizolith impressions, as well as these very simple bryophyte impressions as well in these backshore deposits. So this is of the same bed. This is looking at from the side. This is looking at from the top. So that's also quite cool, is that we're starting to see the rise of terrestriality in the Bokkeveld group. What's also quite cool is that these here are codified plant impressions. So we know that there must have been vegetation on land. So in one of these big storm events, it could have ripped all this vegetation out and threw it into the basin itself. Or alternatively, these could be very catastrophic events that took place on the onshore environments, which need to be explored in future. And yeah, you can see this here is an upper shore face. This is a tabular cross-bedded sandstone. There's this characteristic black color to dark gray in color, and this is because of these codified plants. So there's also these pseudo coals that I've managed to find in the field, which need to be looked at in the future. So moving on to these transgressive, from there, we're now going to these transgressive barrier island lagoon deposits. So these are in the Tratra Formation. So the Tratra Formation is the oddball of the Bokkeveld group, in that it just doesn't do what it's told. So in the field, sort of looks like, here's the top of the Hex River Formation. This is the Tratra Formation, and this is the Boerplaas, which succeeds it. And there's this very interesting sandstone over here, which is a new lithostrat unit that is coming out later this year. This is a Groot Rivier member, but this is quite important. We'll get onto this in a bit. So what we see is a succession of basal tidal flat environments moving into this beach barrier complex environment, which is represented by the Groot Rivier member, and eventually into these deltaic environments in the Boerplaas Formation. So that's the part that we're looking at. So just to jog your memory what these deposits look like. So if you had to go to a barrier island lagoon system, you'd have the offshore environment, more distal parts. You'd have this beach barrier, which by all intents and purposes would look like a shore-faced beach deposit that you would see that I just described. But importantly, behind it, it has this lagoon, as well as these tidal inlet deposits that one sees. So in places with large tidal ranges, this tidal channel and delta complex, this would be a very well-developed type environment. Whereas in micro tidal environments, you wouldn't really see this. So what's interesting with lagoons and beach barriers, you've got this intimate interplay between shore-faced processes, or more say marine processes, and tidal processes. And you can work out which one is more dominant based on the frequency or the thickness of these individual deposits. So I didn't have time to make a more succinct summary diagram, but this is just what that succession of the Tratra Formation looks like. So this has been described in great detail now for a publication that's coming out in SAJG. So it's been reassessed. So yeah, what we'll be looking at first are these channelized tidal flat lagoon environments, which are at the basic succession. So in the field, this is what it looks like. You've again got these non-amalgamated quartz wacky sandstones. Now, generally, when we've seen in the Bokkeveld group, when you put your nose on this, you would expect to see hummocky cross-stratification. But when you put your nose on this, what's actually quite cool is that you start seeing, or that you see these compound cross-bedded sandstones. So these individual sandstones are cross-bedded, but what's quite cool is that they've got these thick mud lags at the top of it. So this is a clear indicator for tidal influenced environments. So this is really, really cool to actually see this. And this, as I say, is the only known Devonian high latitude tidal deposit that is known. So this is quite cool. So what's nice is that you're actually looking at these tidal channels and these tidal flats. So you're seeing these abandonment phases over here, which is quite interesting. What's cool as well, you've got these sand cracks. So some of these that were exposed. So in tidal environments, you have intermittent exposure, and you've got these nice sand cracks that one sees. So this is indicator of desiccation cycles. So not the best picture, but what's cool is that you've got these algal matte textures as well. So this would look very sugary. I had a better photo, but it didn't. My camera just seemed to bugger out. But what's quite cool is that they almost look like a spotty teenager with acne. So they've got the very characteristic impression. So this is very, very cool. What's also interesting in and among these tidal deposits, we've also got wave ripple sandstones. So it shows that intermittently these tidal flats, like what we have in all tidal flats today, during high tide, and if you had a storm coming through, you'd have, or wave action, you'd have wave ripple lamination forming. So it's quite cool. From a trace fossil perspective, what's interesting is that we've got evidence for hohos and nunus that were crawling around as well. So there's these nice Russophycus, Cruziana, Circlichnis, Diplachnites, Didymorlichnis, Monocriterion, the suite of them. And these are nice because they are good indicators of mixing between marine and more stressed environments is what you would expect in tidal flats environments. So that's quite cool. That was the lower part. Then moving up into this here is this transgressive beach barrier. And so this is very, very interesting, what's happening over here. So yeah, so this is what it looks like in the field. So yeah, this arrow is indicating the Groot-Rivier member. And what we do see over here is that there are these 2, maybe 3 upwards finding successions that one's seeing over here is that repeated transgressions were influenced and reworked these deposits. So in the field sort of looks like, this is my geodaddy, Greg Buerta. He came into the field with me at the beginning of this year to help document the stuff. What's quite cool is that the changeover takes place along a very defined boundaries called the wave ravinement surface. And again, you see these non-amalgamated sandstones, but when you put your nose on them, you see hummocky cross-stratification. So you know that there's definitely a change, a big change that's happened over there. Very big transgression has put these more distal environments, wham, on top of these tidal environments. Well, it's actually also very interesting as well with these deposits is that they just look cuck in field. There's no other word for it. When these sandstones become more chunky, you know, if you look at them, there's hardly any internal bedding. They almost look massive. They've got these very funny irregular bedding planes. There's something weird going on with it, with its preservation. So it's actually quite interesting if you think about it. During transgressive regimes, you have a lot of reworking, a lot of sediment bypass. And what you're doing, in doing so, you're actually promoting, you actually bringing, with you reworking sediment quite a bit, you actually are winnowing out more clays out of the system and actually increasing the primary porosity of these sandstones. And because of that, with an increase in primary porosity, you've got these weird diagenetic effects that take place. So you've got more opportunity for secondary precipitates to form. In high latitude environments, these are not carbonate factories. So it's actually interesting is that you've got these iron oxides and other goodies that are precipitating in these sandstones. So very, very interesting. And from a hydrocarbon point of view, if these rocks still had any primary biogenic material, these are the sort of sandstones that would be our major reservoirs. And this is something, of course, that we could forward model to today and looking offshore for these transgressive beach barrier sandstones. These are very good deposits. What's quite cool is that internally, and going back to this in these sandstones as well, we've got these complete preservation of these brachiopod oyster banks. So this is the underside of one of these sandstones, and these are just pitted with all of these little depressions that you see, these little brachiopods that are preserved in their life position. So that's quite cool. There are some plants, these are lycopods, this is a haplostigma that were preserved as well. Some Cruziana, Scolethus, etc. And in some places as well, we're actually seeing preservation of the top sets of these lagoons, these barrier sand bodies. We actually can see plant rootlets preserved. So just to explain how these things formed in this sort of succession, as I was saying previously, in a normal beach barrier setting, if you had to look at it, it would look as if it's in a normal regressive beach barrier. You would see the full shebang like you would see in modern shoreline of typical shore face type environments. But in transgressive beach barriers, it's a bit different. So what happens is, as sea level rises, storm wave base intersects the beach barrier and reworks the beach barrier and spits it over the sand into the lagoon, as well as into the distal environment, reworking it as a lower shore face type deposit. So just to digress, to go back, where you do see primary sedimentary structures being preserved, one sees hummocky cross stratification, low angle cross stratification, wave ripple lamination in these sandstones. So these beach barriers we know have been reworked as storm deposits. So this is quite cool. So in the model that we are proposing in the Bokkeveld group, we're proposing a shore face retreat model. So as sea level rose, as transgression occurred, the beach barrier was reworked and was pushed, part of these sediments were pushed into the lagoon as a washover or as washover fans, or were reworked as low shore face deposits, and these were blown out into the offshore environment. So what's actually quite cool is, based on what you are seeing with your deposits, you can work out the rate of transgression, or not the rate, you can work out the strength of transgression if it was very rapid or if it was very slow. So what's actually quite cool is that now with us documenting these in fine detail, we are now able to actually work out the rate of, or the relative rate of transgression based on the environments that are preserved. It's just essentially the amount of reworking. So we've seen moderate reworking and large or a great degree of transgression. So we're seeing more of this over here, but repeated. But that's a story for another day. And then finally moving up into this upper part. So this is where you start seeing these deltas. This is right at the top of the Tratra Formation going to the Boerplaas. And that's where it is over here. So generally when we think of deltas, we think of river-dominated deltas. So being like the Nile Delta or the Mississippi Delta, but also you also get wave and storm-dominated deltas. So again, in fluvial-dominated deltas, you know, you actually see the fluvial channels. These things are left in peace, you know, to prograde into the basin. You see them. Whereas in storm and wave influenced deltas, these channels are reworked as shore face deposits. So again, this complicates things further. You know, if you're looking at, people would say, well, then aren't all shore faces storm and wave dominated deltas? Yeah, I don't see deltas prograding out everywhere on Earth. These are in specific regions. So yeah, that's a philosophical debate, which we can go into if you guys want to. So yeah, so in storm and wave influence deltas, what you would see is these guys are like half and half. They're fence sitters. So you'd see some channels, some shore face deposits. So in the Bokkeveld group, this is pretty much what we see, is that in these most distal expressions of the distal delta front, we do see these nice channelized sandstones, but at the same time as well, we also see these storm hummocky cross-stratified sandstones here at the same time. So we are seeing both. So this is probably why it's a wave influenced, storm and wave influenced delta. And these, of course, prograde and coarsen upwards from these more distal delta front and pro-delta shales, which succeed the Groot member. Then moving into the most proximal expression, so this is in the Boerplaas Formation. This is at Swartkrans in the Cederberg. So there's my mate Claire Browning up here. There's her for scale. And what we did was that we went out here and we scaled these cliffs to go and study these deposits. So again, these are characteristically black and dark in color because of this high coalified plant material that one sees in it. And typically these are what these deposits look like. You can see some nice cross bedding over here. But what's interesting is that if you put your SEDS goggles on, so this is looking at, both these pictures are at right angles to one another. This is a side-on view of these channels. This is looking down the channel axis itself. So it's actually quite cool is that you're actually looking, you can actually see these channels in 3D. And again, that's what they look like. So the model that we have proposed for this now, why it's forming in the Tratra Boerplaas Formation is that at some point you had an incised valley that formed, probably at the latest Hex River. So you had this incised valley that formed, And then this valley became flooded during the transgressive phase, the formation of these beach barriers, reworking, etc. Then regression set in. And of course, what we are proposing is that there must have been a bayhead delta in the most northerly regions of South Africa. We still have to find these, and these bayhead deltas in these estuaries during regression, these became deltas. So that's the model that we've proposed now. So going into the last part of the talk, you might be saying, oh, that's so cool, you're seeing all these environments, so what does this mean? So, well, that's what I said, thought, but what's quite cool is that if you go and look at the stacking of these environments, and if you know if these things are transgressive or regressive, you can erect a sequence stratigraphy for the succession. So this is going to be revised now. This part has been revised, so the story is more or less the same. So now we've got a sequence stratigraphy across the Western Bokkeveld group, which hopefully if I can come visit your oak site in Overberg, just to see what these more southern exposures look like, to actually see if we can trace them right through, it'll be quite kif. But what's cool is that you can use this to make a, if you know how these things are stacking in space and in time, you can work out a relative sea level curve. So what I did was this, I came up with a sequence strat model, which is in development. And from here, worked out a relative sea level curve at different orders. So these are, I use maximum regressive surfaces. So this is where the most regression took place as sequence boundaries. And I have a hierarchy system. So second order being the largest changes in sea level. Third order, the squiggle over here, being smaller changes in sea level. And then fourth order, even smaller changes in sea level. And we can take this down to fifth or sixth. But yeah, that's a lot of work. So it's for someone else to do in the future. So what these are doing is that they are describing shifts in sea level within shifts of sea level within shifts of sea level. So what these blockies show over here, these different colors of the different environments, how they are migrating in space and time. So this is quite cool. We've got a very high res view of sea level change now. It's the only high resolution sea level change for high latitudes during the Devonian. So the major flooding surfaces, or where major shifts in sea level took place, were here in the Upper Rietvlei Formation, the Hex River Tratra contact, the Boorplaas Waarboomberg Formation contact, and the Osberg Karoopoort contact. So these are where these big shifts occurred, and here's where these smaller fourth order shifts occurred. So in the Gamke Voorstok, Waarboomberg Formation, Hoofdzaal Klippel Kop, and the Upper Klippel Kop. So yeah, again, so this is quite cool that you can actually see this. And then there's also this possible middle Voorstok. There's this member I'm trying to propose now, the Dedorens member. I've actually managed to trace out this particular allo sequence, yes, it's all the way from Calfinia down to Dedorens. It's a very, very particular deposit, but that's a story for another day. So what's actually quite interesting is any of you guys that know Mike Cooper. He used to be quite active here in South African geological circles. Mike Cooper was a bit of a wunderkind. He never did a day of fieldwork in his life. He just read people's theses, and in 1986 he came up with this sea level model for the Bokkeveld group. He said, right, based on depositional trends that he's read about in people in Hannes's thesis, as well as speaking to Tony and co. He took this and he said, right, we can compare this to the global sea level curve. And he proposed this model over here. And what's of interest is that he proposed this, and if the problem we've got with the global sea level curve is that we've got no way to date our succession in high resolution to compare this with. What's actually interesting as well is that if you take his model and you take my model over here, is that they do seem to largely correspond with one another, But then again, this is just matching lines with lines. It could all be wrong, for all we know. It could just be a mere coincidence. Humans like finding patterns, like people who say, oh, there's pyramids on Mars. Look, there's a smiley face on the moon. It must mean ancient aliens. So, yeah, I wouldn't jump and say, hey, no, until we can date this, then we'll take it seriously. But what's interesting on that fact, on that point is, you know, we have to ask ourselves what was controlling these allo sequences, what was causing these shifts in sea level. So if we go back to sequence stratigraphy and we look at changes in stacking and environments through time, etc., is that there are three main factors which control eustacy, or sorry, two main factors.
Cameron.
Okay, 5 minutes, cool, nearly done. Tectonics and climate. So these affect eustacy, but at the same time, sediment flux as well. So we need to look for what these things are. So we have to rule out polar ice caps. They weren't there. So that probably wasn't a cause. Global tectonics and dynamism, that probably is the case. And as maybe as well as shifts in global climate. So that's something that we're going to, I'll leave with today. We've started researching it now to try and figure out what that is, and looking at detrital zircon populations. But yeah, I'll just skip there. You just skip it. So yeah, what's actually interesting is just to show the sequence stratigraphy over here. What's actually interesting is that if you reconstruct the shoreline for each of these sequence events, we see that the shoreline was changing its orientation systematically northwest, southeast, southeast, northwest. So yeah, these things seem to be lining up with pre-Cape structures. And it seems as well as that this basin was reacting probably to flexure. So we're busy working on a new model now to figure out if this was responding to flexure. So we're busy looking at South America at the moment. And what we are seeing so far is that we've got this increase in South American zircons coming into the basin. So long story short, it seems that we are seeing influence of the Famitinian arc in South Africa, and we've got a new model that we're proposing now, is that the Cape Basin was actually a fallen basin. So from this over here, you go to Falklands, you see this La Malvinas son Argentinas. The Malvinas Islands are brothers of Argentina. They belong to Argentina. But what we're starting to see now is that El Cabo son Argentinas, we're actually starting to pick up now. It's influence from South America that's affecting sedimentagenesis and tectonics in the Cape. That's a story for another day. So yeah, thanks very much, Oaks. And then just thanks to everyone over here that sponsors this work. Really, it's cool that people want to give money towards this, so this is great. And yeah, thanks very much, guys.
Thanks, Cameron. That was fantastic. Can you all hear me?
Yeah, I can hear you. Let me just stop starting. I just need to stop sharing the screen and figure out how to do that.
Okay, so people are welcome to put their videos on, and we'll have some questions. Gert, are you going to look after the questions for us?
No, you go ahead, John. I'm not the host. I'm not a host. I haven't been assigned a host. So either Cameron must do it or you must do it.
Thanks, Cameron. That was excellent. I have a couple of quick questions. First of all, thanks. When are you available for a field trip? Because I'm sure there's a lot of us that live here in the Overberg would love to get you out there and look at our geology, and then also take some time and go and spend it in the field with you. So my second question, have you got a new glossary that's been accepted for your geological interpretations? Quite fascinating. Is chowing and wooded and cool and goodies all being accepted?
Yeah, no, it's the neurons, they misfire sometimes too quickly, so I struggle to find the word. So, but John, wooding, clapping, yeah, you know, it's all that sedimentology is about. Yeah.
Yes.
There's a Mike DeWitt in there, but it's obviously not that Mike DeWitt. Tony Boniface.
Cameron, can I ask you how much of this has been published?
Quite a bit of it, eh? So the main stuff from the sedimentology, there's 2 papers in JSR that have been released in the past 2 years. There's another one coming out in SAJG. It's coming out in issue 123.3. That's on the Tratra Formation.
So that's a Journal of Science.
Yeah.
Geology, yeah.
Yeah, so there's that, and then I've got another 2 or 3 coming out later this year. So one's on the biogeography of these brachiopods and this extinction event.
It's research, obviously.
Okay.
Yes.
Right. So can we have people raise their hands? Do you have the system? If you go to the participants, we can use the hand raise system, and we'll get some more questions going. Who's next?
I think it's Jean.
Okay.
Cameron, hi, Jean. I'm joining you guys out of Yorkshire here in England, and I've been part of mapping the southern portion of the Worcester sheet, as well as the Riversdale sheet. So the challenge there was to really see what was left in the ruins by these farmers that wasn't ploughed up. And I've done my best to subdivide the Ceres and the Bido in different sandy units. So I love you to bring your knowledge down south into the Overberg and come and show us how some of these units would definitely be correlatable. So I should be back in South Africa end of the year next year, and I'd love to meet you up in the field, and we can go and visit some of those things.
No,
so
definitely.
That's my input.
No, I'm a big fan of your work. I mean, you're the same John Milan that did the Nardo subgroup descriptions, eh?
Yes. I did a bit of that, and then the South Coast Geology on the Bredasdorp, and then the oil industry swallowed me. So
oh, lekker. Earning big bucks now.
He's been furloughed though.
Yeah. I see Mike.
Yeah, hi, Cameron. Thanks very much. Very interesting talk. I just wanted to ask if there's any evidence for turbidites in the area. I don't know how deep that Tankwa rise is in the Agulhas Basin, but are there evidence for turbidites in that area or not?
Okay, I'll let you guys in on something that's coming out in the Wuppertal Formation. We see there's a thin, it's maybe about 10-meter thick succession of possible turbidites over there, and those turbidites seem to be associated with a massive extinction event in the basin. So there's something catastrophic that's happening. So I'm trying to get Deville to come out to just verify this, but it's very exciting, and these things look like they are hyperpycnal flows. So something shed, sediment full force. It must have been a more of a big regression that just dumped all the sediment.
I was wondering if there's any anoxia there, because it seems to be very, very black in some places.
So the darkness over there seems to be a control of illites. So with the formation of the Cape Fold Belt, you've got a lot of these illite clays that have formed, and that's generally what seems to be the cause for blackness.
Illite clays, the clays that are further up towards Caledon and these places where you have those purple clays, are those lithium based or not at all, or is it rather the degradation of iron?
I have no idea. That's for someone who's much more smarter than I am and more chemically inclined to have a look at in future. But it is interesting because especially when you look at the Klip-Kop formation, you see these fantastic, marvelous colors in the rock, and you see these little nodular concretions and horizons. And I've always thought these things, you know, they must be SEDEX or BMS type things, what they could be associated with. And I know that there was a sort of a skunkworks project that was undertaken by the Geological Survey and UPE here in, I think, the late 60s. This is what Saki Risk told me about. And he says that they documented some of these things, but then the project was mothballed.
Yeah, those are SEDEX deposits that he was talking about there. These are very, very young. If you go out toward Culloden, they're extremely young. They must be 150,000 K old. But
yeah.
the gradations of colors within those clay banks are quite astounding, and there's a lot of nodulation there as well.
Yeah. It might be a worthwhile thing to look at in future. If there's funding available for that, I think it would be a good project to do, just to figure out. The only sort of alteration type project that I know of was by, what is his name? The late Hugo Ferri. He did that for his MSc a couple of years ago, but he didn't publish it. He just mentions that all this alteration that took place and causes for it, but it wasn't taken further. So I think there is scope for that.
While I'm hogging the show here, I hope the other guys don't mind, but those brachiopods that you find, I found quite a lot of them out towards Lady Smith. Have those beds been turned on their side? Because the indication to me was that the shells are actually all pointing downwards. If you look at the attachment point, the attachment point seemed to be all at the bottom, and the whole bed turned on its side. Is that true, or have you not found it?
Pretty much, if I had to use my hand and my arm as a brachiopod, brachiopods, they've got two valves. So you've got a pedicle valve that normally sits at the top and a brachial valve at the bottom. So what's interesting is that the pedicle is what it mounts itself into the sediment. And then this thing, you know, will open and close its valve as it eats. So generally what will happen is that the pedicle foramen and the pedicle point, that's what would make contact with it. So the impression that you'd see sometimes when it's in place, you'd see of the brachial valve and then of the pedicle foramen going into the beak, going into the sediment. That's if it is articulated. So that's how they would sit in life.
Thanks.
John?
Yeah, anyone else?
I think it's John James.
Yeah.
Yeah, Cameron, just a quick question. When I did paleontology, lamellae branches and brachiopods were considered to be totally separate families. I understand that's changed. Could you possibly enlighten me slightly on that?
No, lamellibranchs and brachiopods are very different. They are, you know, they're extremely different from one another. So they're two separate branches on the evolutionary tree. So the only thing that they have got in common is, yeah, they so very, very basal in the actual family tree itself. Even, yeah, they're fundamentally very different, right from the way in which their structure, their life histories, etc. They're very, very different. So one is a trocho. See, I don't want to use too much technical words.
Be all right,
but yeah, one is a trochophorate. That one's a lophophorate. So they feed differently. Structurally, they're very different. Yeah, they are very, very different animals.
Thanks. That just clarifies it for me. My recent readings seem to say they've changed the naming over the last 10 years or so, but that's fine.
If they had to change, if anything had to have changed, it would bugger up some ideas that I've got. So I'm glad there hasn't.
Okay. Any more questions there? Carry on, Cameron. Any more questions? You see any more hands?
Just busy scrolling through it now and just checking the pictures. No, it doesn't seem as if there's any more. Jean's got another one.
Okay.
Just more a general comment. We started off with guys mentioning the color of the Bokkeveld and the shales and those things. And I mean, once you come back to the Overberg, and with these large excessive weathering profiles, you know, and locations called Rooi Hoogte, Geelkraans, Verfjeuwel, and around the Albertina area, there it was actually these pigments were mined, and in the early days. So who knows? You know, we might sit on top of something commercial in our area.
I think we must just keep it quiet. Yeah, don't tell anyone about it being mineable. Yeah, we'll do that.
Okay, has everyone had their bit?
Looks like it.
Okay. So thanks, Cameron. That was fantastic, and I'm sure there'll be lots of follow-up, and people like Mike Dormer will certainly be on your case as well. There's just a wealth of info, and it's on our doorstep, and we need to go and get stuck into it. And I think for me, the last takeaway is it shows that, you know, the basic geology that was all done by people in the past, and there was some really good geology, laid the foundation for you know, much more work, and particularly the sort of work and the detail that you are now doing, and the way you're putting apart, you know, unit by unit is just fantastic. And that's what we need to be doing in every one of our geological sequences, you know, throughout the country, be it the Bushveld or the Wits or whatever. So well done, and appreciate your time, and we look forward to further engagement. Thanks a lot.
Thanks. What I can do before I leave, what I'll do is, if anyone's interested in those papers I mentioned, I'll email them to you and Henny, and then if you guys want to distribute it out, by all means. So I can share those with you guys.
Yeah, I already have some of your papers, and would you be all right with sending us a PDF of your talk? Just, you know, you'll have to compress it to the minimum.
Yeah.
Is that possible?
Yeah, I'll sort that out.
We can pass it on as well.
All right, lekker.
Okay. Thanks, everyone.
All right.
Thanks, Eddie.